Well, what we're going to do to build on yesterday is we're going to take measurements, values, numbers. We're going to do computations today, but we're going to pay special attention to performing those computations while we preserve the correct number of significant digits. And I'll show you why that's necessary in a couple of examples. Here's what we want to do. Two primary things we want to work on today. We want to perform the operations on real numbers, and we want to make sure that we keep the correct number of significant digits in your result. You can't have a result of a computation that's more precise or has better accuracy than the information you start with. And then we're going to look at a couple of simple applications where you can see why significant digits are reasonably important. And again, we want to make sure that we report our answers with the correct number of significant digits. I'm going to start out with an example to let you see kind of why this is necessary. Let's go back to our town with a population of 15,000 people again. Here's what happens. The town has a population of 15,000 yesterday, but today, property taxes got a little bit too high. One family is fed up. A family of 5 moves out of town, leaves the house vacant. No, better yet, they burn it down and then leave town. Add some drama to this story. So we just lost 5 people. Now, would it be correct or fair to say that the new population of the town is 14,995 people? Well, a lot of you are shaking your head no. Why not? 15,000 may or may not, probably not, was exact to begin with, right? I mean, the population was somewhere around 15,000, so we didn't claim to know the exact population here, so how can we possibly claim to know the exact population after they move out? Make sense? Well, what's the problem? What's our precision here? Here we're only precise to the nearest 1,000. We are only estimating the population of the nearest 1,000 people, so we can't very well suddenly lose 5 people and claim that our precision is now to the nearest person, right? There's a problem there. Well, in fact, what would you claim? This is not a realistic answer for this problem. We can't claim that it's 14,995. What would you really have to claim the population of that town is after the 5 people leave? You'd still have to say it's 15,000. Those 5 people really don't matter. They are not large enough to affect the precision that our initial measurement was with. Well, that presents us with the rule for addition and subtraction of numbers when working with significant digits. When you're adding or subtracting decimal numbers, your result will have the same precision as the least precise number that you worked with. In other words, your answer can't be any more precise than any of the numbers you were adding or subtracting. If our population was to the nearest 1,000, we certainly can't get a result that's any more accurate, any more precise than the nearest 1,000. Saying that a different way, the least precise of the numbers being added or subtracted determines the precision of your result. Let you get caught up with that, and then we're going to go back and readdress the population question. We kind of already did, I guess. We got a little bit ahead of ourselves. So, in this example, we're subtracting 2 numbers. We're subtracting one from another. The precision of this one was to the nearest 1,000. The precision of this one was to the nearest whole person. Which one is least precise? That one. So our answer can't be any more precise than that. that means that we have to take our answer, 14,995, and round it off at what precision? We have to go back and round it off to the 1,000. And so if we take 14,995, we do the computation, it's just that we have to, when we're done, round it back to our least precise number here. And if we round this off to the least precise spot, that's the nearest 1,000, we'd have to round this off to the 1,000. We would still have to claim, as you told me a minute ago, that the population of that town is still 15,000. Does the basic principle make sense why it has to be true? You can't start out with something that's not very precise, do a little math with it, and make it suddenly precise. It just wouldn't work. Okay. Well, this is one for you to try. I'm going to give you a minute to do this. Let's say you've got a small fuel cell. Little tank, holds a small amount of liquid fuel, and it has an empty weight of 945.562 grams. I should have written empty mass there. It's a slight misstatement of terms. It should be an empty mass of 945.562 grams. We want to find the total weight if we add 362.7 grams of fuel. And we want to report the answer with the correct precision. That is to say, the correct number of significant digits. Okay, let's take a look at it. First of all, we just do the math. We look at the significant digit situation when we're done. But if you add these together, you get 1,308.262 grams. But we can't keep all that precision. This number is far more precise than this one is. In fact, where are we going to have to round this off? 1,308 point what? 3. This one is only precise to the nearest tenth, so that's our bottleneck. That's what limits us. And so we have to round this off at the nearest tenth, and we would say that the new weight, new mass, 1,308.3 grams. That's the correct number of significant digits. Any more than that would be claiming that we know the total weight more precisely than what we really do, because this doesn't say any more specifically how much fuel was added. So we've taken care of addition and subtraction. Questions so far, or does that look okay? Yep, you use typical rounding rules. Once you decide where you have to cut off your answer, where you have to round, you just use traditional rounding rules. Since we are limited to the tenths, we'll just look to the right. Since it's a 6, that 2 will get kicked up to a 3. Yep, typical rounding rules. Okay, we're going to do the same thing for a couple different operations. We're going to do multiplication and division, which have the same rule, powers and roots, which have a different rule, and reciprocals. And they're all fairly simple rules to follow. Multiplication and division. Well, when we multiply and divide, we've got to follow a slightly different procedure. No more difficult, but different. When multiplying and dividing, which is probably the more frequently used operation, we don't pay attention to precision. We pay attention to the accuracy, the number of significant digits. The factor or number within our multiplication or division that has the fewest number of significant digits determines the number of significant digits in the result. Their location doesn't matter in multiplication and division. All that matters is how many of them you have. before we do this problem, I just want you to think about an example of, well, never mind, I'm getting ahead of myself. Let's just do this problem, then I'll show you the thought rolling around in my head. Okay, well, first of all, again, multiplication and division, we don't pay attention to where the precision is. All we do is count sig digs. So in this number, we have 4 sig digs. Over here, we have 3 sig digs. How many sig digs will we be allowed in our quotient? Just 3. Yep. We can't have any more sig digs than the fewest number of sig digs in any of the numbers we're working with. So, I had that. If you do that division, hopefully you come out with, let me know, anybody come up with it? -3 point. If we leave plenty of extra ones here, we'll cut it off properly in a minute, but 6575? Okay, now that's too many sig digs, right? Okay, well, we can only keep 3, which means we're going to have to cut it off right there. Follow typical rounding rule. What would be the correct quotient here? -3.66 would be the correct number of significant digits. Here's an example of why that works, or why that rule has to be true. Already got that one if I erase it? Okay, here's an example of why that's true. I wouldn't put this in your notes. It's just a point for you to try and understand why that rule exists. Let's say that again. Let's go back to our good old town with population 5,000, or let's make our population 5,000 people. Okay, now let's say that this town is going to collect a $1.25 curb painting fee from every person in the population for keeping the curbs painted nice and yellow. So we're going to take our 5,000 people and multiply this by $1.25. Each person has to cough up $1.25 to live in a city where the curbs are neatly painted. How much money is that going to generate for the city here? $62.50. Would it be fair to say that this city is definitely going to generate $6,250 from this curb tax? No. Why not? Yeah, we don't know that there's really this many people in the city. We only know that's how many there are to the nearest 1,000. So it wouldn't be fair to claim that we're going to get this kind of accuracy in the total collected taxes. In fact, what would we have to call this? How many sig digs have we got here? 1. How many here? 3. So our answer is limited to how many sig digs? 1. We'd have to call this $6,000. City's going to generate around $6,000. We can't claim to know any more accurately than that how much money they're going to generate. Does that make sense? To do so would be misleading. Here's a problem for you to work out for practice before we move on to the remaining operations. The density of copper is 8.92 grams per cubic centimeter. I want you to find out how much mass you have if you have 105.5 cubic centimeters. So each cubic centimeter has a mass of 8.92 grams. I'd like you to find out what the total mass would be if we have 105.5 cubic centimeters. And I want you to report your answer with the correct number of significant digits. I'll give you about 2 minutes to work that through, and we'll take a look at it together. Okay, well, we're going to multiply those two values together. We've got 105.5 cubic centimeters. Each cubic centimeter weighs 8.92 grams, has a mass of 8.92 grams. Multiply that, you get 941.06 grams. Is that correct, or is that claiming too much accuracy? Too much. What do we have to write the answer as for the correct amount of accuracy? We have to, let's see here. What do we write it as? 941. How many sig digs? There? So we're limited to 3. We have to call this 941 grams. That's the best we can do. Okay. So we know what the rule is for addition, subtraction, multiplication, and division. Powers and roots we're going to deal with tomorrow. Tomorrow we're going to focus on powers of roots. There's one more operation that we're going to look at today before we conclude this lesson, and that is a reciprocal. You remember what a reciprocal is? What's a reciprocal? Yeah, there's two definitions. If you have a fraction, it's just flipping that fraction upside down. If it's just a number, it's 1 divided by that number. In general, you find the reciprocal of a number, regardless of whether it's a fraction or not, by taking 1 and dividing it by n. So if we have some number n we want the reciprocal, we take 1 and divide it by n. And yeah, the reciprocal of a fraction a over b is b over a. That's probably the first definition of reciprocal that you learned because you need it to divide fractions. And the rule for taking a reciprocal is very easy. It's good news. When you take the reciprocal of a number, you just keep the same number of significant digits that you start with. So let's take the number 0.450. Let's find out what its reciprocal is and preserve the correct number of significant digits. Well, the reciprocal would be 1 over 0.450. We really don't work with pure fractions that much. Technical fields, almost everything we do is in decimals, so most of our examples will be with decimals. So we're going to take 1 divided by 0.450. Now, how many sig digs are we starting out with here? 3, good. I don't think I heard anybody say 2. That's right, there's 3. That 0 is significant. It shows additional precision. Okay? So we have 3 sig digs, 0.45, and we want the reciprocal of that. You should end up with 2.2222. But we can't keep all that precision. What do we actually have to say that our reciprocal is? We have to say that it is 2.22. 3 sig digs is the best we can do there. So the rule for reciprocals is nice and simple. Here's a real quick application. Let's say you've got a runner, pretty good runner, heck of a runner actually, could sprint at a rate at 9.70 meters per second. So the question we want to answer is, how long does it take the runner to travel 1 meter? Well, taking the reciprocal flips your units upside down if it's a number with units. So for example, if we take the reciprocal of 9.7 meters per second, Our answer will be in seconds per meter. We're going to work a lot more with units and how they behave in computation in a few weeks. But for right now, if we take the reciprocal of 9.70 meters per second, we'll have the number of seconds per meter that it takes that runner to travel, how many seconds for each meter. Well, what is the correct reciprocal with the right number of significant digits? We'd say that he's traveling at how many seconds per meter? 0.103 seconds per meter. That's right. Started out with 3 sig digs. Take the reciprocal. We preserve 3 sig digs. Good. Now, just as a short review of math that you've had before, what if you've got some of these operations combined? We're not going to have too many combined operations types problems until a little bit later. But we did addition subtraction rule first, then we did multiplication and division rule. And now we just did reciprocals. In general, this is just to brush up, see what you remember from math. There's basically 4 main categories of mathematical symbols that we need to dual with. So we're going to call these our order of operations. Do you remember what they are? If you have more than one of these operations to do, you do them in order, keeping the same number or the correct number of significant digits at each step. The first thing you would do is you always do your grouping symbols, and that usually includes parentheses first. Then you take care of your exponents and roots. After your exponents and roots are all taken care of, you move on and do multiplication and division. That includes any reciprocals. And finally, you do addition and subtraction last. Okay, we're going to look through just one problem here that has more than one operation involved with it. We'll work through that and report the correct number of significant digits, and then we'll wrap up. Everybody have those? Okay, let's just do one short example here. Let's suppose we have this problem. We've got 44.64 plus 1 over 4.65 times 12.31. We want to evaluate that, find out what the overall value is, but we want to do it preserving the correct number of significant digits. Well, what's the first thing you have to take care of here? One over 4.65, right? Got to do that first. So let's rewrite it and rewrite that part of it with the correct number of sig digs. 44.64 plus, what does that work out to here? 4.65. The reciprocal with 3 sig digs will be Somebody verified that this is correct. 0.215. Does that look okay? Now we're going to multiply that by 12.31. We have to do the parentheses next here. So we're going to take 0.215, 3 sig digs, times 12.31, 4 sig digs. And what do we get for a product here? How many sig digs can we keep? 3? 2.65, that's right. So now we're going to add these two numbers together. Goes back to addition and subtraction. When we add these two together, are we paying attention to the precision or the accuracy when we add? It's the precision, where the decimals occur. Hundredth, so we're certainly safe to keep to the nearest hundredth precision. And I have 47.29. Anybody else have the same thing? Good. And we're done. That's the correct number of significant digits on that computation. Now, it's worth noting that a lot of programs, a lot of disciplines have slightly different significant digits rules. Sometimes, and this is the rule that we'll use, we would just use a shortcut rule. We're not going to yet, but later on in chemistry this is often done, physics this is often done. You use kind of a shortcut rule that gives you the same result most of the time. You would just look at all these values to begin with and count how many sig digs in each one. This one has 4, this one has 3, that one has 4. You would look at this and say, well, 3 is the lowest number of sig digs, so I'll just report my answer with 3. Doesn't always give the same result, but for most practical purposes, it works. We're going to, for right now, follow this through in detail like we did, and then later on when we do more computation, we'll start using a shortcut. Okay. The last thing to note here before we wrap up is the one exception to the sig dig rule. There's one very simple exception that you need to be aware of, and that's this. There are certain numbers that are exact values. For example, how many cookies are there in a dozen? We'll say a traditional dozen. There are 12, right? Now, does that mean there's somewhere between 11.6 and 12.4 cookies in a dozen? No, there's 12, exactly 12. You could say 12.000 if you wanted. There are certain things that are exact. And even though we don't put a lot of zeros after the decimal point, we know they're exact. They're considered to have an infinite number of significant digits. Here's another example. 1 foot is 12 inches. We don't have to say 1 foot is 12.000 inches. It's exact. 1 meter is exactly 100 centimeters. You could consider an exact value like this to have an infinite number of significant digits, because we could put 12.00000 all day long and it would still be true. When we're doing computations with exact values do not play a role in determining the accuracy or the precision of the result. We skip them. We pay attention to all the measured values, but exact values are not contributors to how accurate or precision our result can be. Here's a simple example of this. Candy bar. You got a certain candy bar. Let's make it Mars bar. They're the best kind after all. Mars bar. Sweet caramel, almonds, and nougat. 152.7 grams each. Okay, that's how much each candy bar is. We're going to take 4 of them, eat 4 of them. That's lunch. We want to know what the total mass is. Now, 4 candy bars, that's exactly 4 candy bars. When I do this multiplication to find out what the total mass of this candy is, I can't say, oh, I can only round this to one significant digit because this 4 is exact. I could write 4.0000 candy bars. Does that make sense? So the only number that we need to pay attention to how many significant digits there are is this one. This doesn't play a role because it's exactly 4. So if we multiply that out, we get 4 times 152.7 grams. How many sig digs will we be allowed to keep in this answer? 4. We end up with 610.8 grams. And we can say we have that much precision, that much accuracy with confidence. Because we knew that's what we had here, and we knew that that was exactly 4. It's not roughly 4, it's exactly 4. This will be a factor when we do conversions in a few weeks. We'll do many conversion factors, and many conversion factors are exact. So those conversion factors don't play a role in our counting of significant digits. Well, that's where we're going to stop for today. We're going to move on and handle powers and roots tomorrow.